Hey folks, how's it going? In this section, I would like to talk about infinite limits. And so what does that mean? Let's do a numerical limit problem and determine what this is talking about. So we've got a function f of x equals 4 divided by x plus 1. That's a rational function. And notice I'm asking for you to find two different limits. Remember, you read this one, the limit is x approaches -1 from the left side. Remember that little negative up there looks like an exponent. That means the limit is from the left side. So we're getting closer and closer to -1, but less than -1. So we could pick our own values. Remember, you're just trying to get closer and closer to -1. So a value that's fairly close to -1, but not -1 and smaller is -2. That's definitely on the left side. Or you could plug in -1.1. That's even closer, right? Or -1.01 is even closer. Remember, this is from the left. And then -1.001. We could try those. I'm not going to make you suffer through me typing this. I'm going to pause it and type those results in, and I suggest maybe you pause it as well. So let's pause it and run these numbers. Remember what we're doing. If I just plug one of them in, we're doing 4 divided by -2 plus 1. Okay, that's this first one. So that's 4 divided by -1, which is -4. That's, without a calculator. But the remaining was, just to save time, I'm going to use a calculator. Stand by. All right, so that was fast, right? Plugged in -1.1, and I got -40, whereas -1.01 is -400, and -1.001 is -4,000. So what's happening here? Okay, what's significant is these numbers are getting smaller and smaller and smaller, so it appears that they are approaching -infinity. And that's correct. Now remember what that means about the limit value. I mean, this result is -infinity, but that means the limit does not exist, right? That's the answer. The limit does not exist, but this is how it does not exist. So sometimes does not exist is not enough information for you to have to know the properties, for you to know what's going on with that function, or the characteristics is a better word. So -infinity is how this limit does not exist. Let's try the other side, okay? So notice here, second question, limit is x approaches -1, but this time from the right side. So I'm going to plug in numbers larger than -1, but approaching -1. Now one number we know that's definitely larger than -1 is going to be 0. You can plug that in, or you could be closer, like, I don't know, how about -0.9? But a little closer would be -0.99. And even closer would be -0.999. You get the point? But that's on the right side of -1. In other words, just a tiny bit bigger than -1. So if I plug in any of these, I don't think you need to see me do that. It's just like when I plugged in -2 down here. So I'm going to pause it, fill those in, and we'll take a look at what's happening on the right side of -1. There we go. So I ran all those calculations, and this is what I got. You got in plug in 0, you get 4. You could do that in your head. -0.9, I got 40. But the closer I get, notice the larger the values get. I bet you could guess if I plugged in -0.9999, I would get 40,000, right? So these numbers appear to be getting larger and larger. In other words, going to positive infinity. Now that's not the answer to the limit. The answer to the limit is it does not exist. So keep that in mind. If it goes to plus or minus infinity, truthfully the limit does not exist. Once again, this is expressing how the limit doesn't exist. So be prepared anytime you're asked, or anytime you calculate a limit and it doesn't exist, be prepared to tell how it doesn't exist. Is it because the left and the right don't match? Is it because it goes to positive infinity or negative infinity? And this is your first infinite limit. That's what this really is. If you get infinity or negative infinity as a result of your limit, which means it doesn't exist, that is an infinite limit. Okay, so what we have here is the formal definition of infinite limits. Don't stress, I'm not going to make you do problems using this on the test, but I am going to ask you to do this for the limit definition, but not for infinite limits. But I do want you to understand this rigorous definition. So let f be a function that is defined at every real number in some open interval containing c, remember it doesn't have to be defined at c itself, it says that the limit as x approaches c of f of x equals infinity. Here's what that means. That for each m greater than 0, there exists a delta, remember delta is a small number, such that when f of x is bigger than m, whenever 0 is less than the absolute value of x minus c is less than delta. So let me kind of just draw you a picture of what's going on here. And then I won't torture you with it much more, but let me just draw you a picture. Okay, so we've got a function, and we can see that this right here, this function that goes to infinity, right? So it goes up to plus infinity. That's what we mean by an infinite limit. So this value right down here is the c. So as we approach c, in this particular instance, just from the left, I didn't graph anything on the right, as we approach c, it goes to plus infinity. So we're matching what we know the answer should be. Now, if I set up all of this information, like what is m and all that, so it says that for each m greater than 0, so if you pick a random m, it could be a really big number, okay? A massive number for m is greater than 0. There exists a delta. Now remember, delta is along the x value. Greater than 0, it's positive, okay? The reason it's positive is because delta is a distance, such that when f of x is bigger than m, okay, whenever 0 is less than x minus c, remember this is c, is less than delta. So here's what we're going to do. We're going to think backwards. So I track over to my graph and find out this tracks back to here, okay? Now this distance right here between my green value, okay, and my c is delta. So that short little distance is my delta distance, okay? Now, if I pick any f of x bigger than m, so don't lose me, hang with me, okay? This f of x, any value bigger than m, so that means up here somewhere, and I backtrack, notice that's going to fit within that delta distance. And anything bigger than that is going to fit with that. But that wouldn't work if that weren't going to plus infinity. Negative infinity has a very similar definition. It just has to be different because we're talking about negative infinity. I'm not going to draw a picture for that, but it's the same idea. So the limit is x goes to c if f of x equals negative infinity. And that means that for each n greater than 0, there exists a delta greater than 0. So again, delta is a distance. So that when f of x is less than n, and I said I wasn't going to draw a picture, but yes I am. Okay, watch this. First of all, let's say we have a graph going to negative infinity. So see that guy's going to negative infinity, right? Now it says for each n greater than 0, there exists a delta greater than 0, such that when f of x is less than n. Okay, so let's just say n is right here. Okay, now we backtrack, right? That takes us right here. By the way, this is our c value. I didn't mark our c. So here's our c value. Now, the distance between c and there is delta. Now, if it says for f of x less than n, so I'm talking about numbers smaller than n, okay, and then I work backwards. Okay, notice that come back down, that fits between c, that x is between c and the delta distance away, so it's the same idea. I did a better job of explaining the plus infinity, but the minus infinity works the same way, okay? Now again, notice I point out, this does not mean the limit exists. It does not exist, but this is a statement of how the limit doesn't exist. Now this is a problem more like what you'll be dealing with. Determine infinite limits from the graph, okay? So we have f of x equals 1 over 2 minus x. Notice I didn't ask you for a limit at all, but if I ask you to take the limit as x approaches 2 from the left of 1 over 2 minus x versus, let's do a cool color, like purple. Okay, the limit as x approaches 2 from the right of 1 over 2 minus x. So how are we going to handle this? You know what to do. So first of all, we're looking at 2 from the left. So first of all, where's 2? 2 is right here. It's a problem, right? 2 plugged into this thing gives us a 0 in the denominator. So we know the limit doesn't exist. But in what way does it not exist? So if I approach 2 from the left, we're talking about this side. I get closer and closer to 2, and I'm asking you, what are the y values doing? Look, they're getting higher and higher. You see that? These guys are getting taller and taller and taller and taller, and it goes to plus infinity as x approaches 2 from the left side of 2. Okay? So the answer to this problem, okay, is tricky. It's not plus infinity, right? It does not exist. So keep that in mind, but that's how it doesn't exist. On the other hand, let's take a look at the next one. The limit as x goes to 2 from the right side. So this time, I'm getting closer and closer to 2 from the right side. Well, what is the graph doing as we get closer and closer to 2? Well, you see it, right? The graph's going down as we get closer and closer to 2. So what does that mean the answer is? Well, we need to write negative infinity, yet, what is the answer? It does not exist, right? The negative infinity is how the limit doesn't exist. All right, so I got a couple of definitions for you, or a definition and then a theorem, okay? So the definition of vertical asymptotes, y'all know what these guys are, you've seen them before. If f of x approaches infinity or negative infinity as x approaches c from the left to the right, then the line x equals c is a vertical asymptote. I left out the word a. I think you'll forgive me. Of the graph of f. Okay, now we already know what those guys are. If you have a rational function at a place where the denominator is equal to 0 after it's been simplified, you have a vertical asymptote. Okay, so right here we have a vertical asymptote. They could both go up to plus infinity, one could go down, one could go up, they could both go down, it doesn't matter. That's a vertical asymptote, and in this case, that would be at x equals 2, okay? But we finally have a formal definition. Before, I know it might have felt like a formal definition, but we just knew that the graph went up to infinity and down to negative infinity. But now that we have the language of limits, it's a rigorous formal definition, because we know that the limit approaches infinity. Okay, now we have a theorem, Theorem 1.14. If f and g are continuous on an open interval containing c, okay, so f and g separately are continuous, okay, and if f of c is not equal to 0 and g of c is equal to 0, and there exists an open interval containing c such that g of x is not equal to 0 for all x not equal to c in the interval, then, I know that's a lot, right? H of x is equal to f of x divided by g of x has a vertical asymptote at x equals c. Basically, what this is saying is if you have a number over 0, when you take your limit value, okay, then you're going to have a vertical asymptote. Remember, 0 over 0? Nope, that's not a vertical asymptote. That means that your function simplifies. But if you have a number over 0, okay, you notice it says f of c is not equal to 0, so that's after you take your limit and you plug the c value in, and g of c equals to 0. It has a vertical asymptote at x equals c. Okay, hence how to find vertical asymptotes. This is what you need to know right here. Simplify common factors if possible. In other words, if you have x plus 2 in the numerator and x minus 2 times x plus 2 in the denominator, you don't have two vertical asymptotes because those guys cancel, right? You only have one, and it would be at x equals 2. So any x value where the numerator is not equal to 0 and the denominator is equal to 0, you have vertical asymptotes. So I have these problems to calculate the vertical asymptotes. So remember what we're doing. I have your steps over here again. Simplify common factors if possible, and then any x value where the numerator is not 0 and the denominator is equal to 0 is your vertical asymptote. Okay. Now the question is, on example I, does that simplify? Can we cancel any common factors? And notice there aren't any common factors. Okay. The denominator is factored. It'd be x minus 3 times x minus 3 times x minus 3, and we certainly don't have an x minus 3 in the numerator. All right, so now the next step, although this doesn't express that completely, the next step is to basically set the denominator equal to 0, because we need to know where the denominator is equal to 0, and then we've got to consider that that doesn't make the numerator also equal to 0. Now, to get rid of that third, we can just take the cube root of both sides, so essentially that gives us this. Or you could write it out 3 times, and you would have that 3 times. So x is equal to 3. Now, if I substitute 3 into the numerator, there's nowhere to substitute it, right? So that would give us 2 over 0 if I plugged 3 in. Therefore, we have a vertical asymptote at x equals 3. Okay? Seem reasonable? All right, let's try another one. So 3x over x squared plus 9. Now, does anything factor here? Can we simplify? Can we cancel this x and this x? Please don't say yes. You can't, right? Because you can't cancel part of addition or subtraction. X squared plus 9 doesn't factor either. Even if it did, it wouldn't cancel with the 3x. So we can't do anything like that. But we can set the denominator equal to 0, because we need to know where the denominator might be 0. If I subtract my 9, you might notice right off the bat I have a problem, because I have to take the square root of both sides. Remember, we need the plus or minus, but that doesn't give me a real number. Okay, not equal to a real number, so that result is out. So you know what that means? There are no vertical asymptotes in this problem. Okay, more of the same question. Find vertical asymptotes. Okay, now we've got to simplify this one. X to the third minus 8. X to the third minus 8, I know you don't see that very often, but that factors. That's a difference of cubes. So if I write this out factored, remember you take the cube root of each term here. So the cube root of x to the third is x. The cube root of 8 is 2. Then you remember what you do. You square the first term. You change this operation, so that'll be plus. You multiply these two terms together, 2x, and then you square the last term, and that's always addition. So you might need to look that up, a difference of cubes. And that's divided by x minus 2. Those cancel. So this function is identical to this function except at one place, at x equals 2. But what that means is our new function is this. If it helps, you could say it's over 1. So can the denominator ever be 0? Well, no. So this is out. You know what that means? No vertical asymptotes. So what's going on at x equals 2? So that's the real question, right? Remember when it cancels, when your common factors cancel, whatever that made that function undefined creates a hole in the graph. So the function's still not continuous at x equals 2. And remember, we called that a removable discontinuity. Now, it didn't ask for that. It asked for vertical asymptotes, but we want to talk about it all the way, right? So next problem, t squared minus 2t over t to the fourth minus 16. Why don't you pause it for a minute, work that one out, see how it goes. And if you notice, that simplifies. So if I factor out my common t, that'll be t minus 2. So greatest common factor is what I did there. The denominator, that's a difference of squares. Okay, so the square root of t to the fourth is t squared. The square root of 16 is 4. Remember, for a difference of squares, one factor is adding, one factor is subtracting. I still don't see anything that factors, but I'm also not finished simplifying. That will factor again. This one won't. A sum of squares does not factor, but a difference of squares does. So the t squared plus 4 is still a result, but t squared minus 4 is now t plus 2 times t minus 2, and now you see finally I've got common factors there. So this function is equivalent to this function up here, except at one place. At t equals 2, which is the factor of the 0 for the factor we canceled out, we have a hole in the graph. So back in red, t equals 2 is just a hole. It is not a vertical asymptote. On the other hand, right here, if I set t plus 2 equal to 0 and I solve, I get t equals to negative 2. Y'all, that's a vertical asymptote. Okay, because if you plug in negative 2 in the numerator, you do not get 0. but you do get 0 in the denominator. What about this? If I set t squared plus 4 equal to 0, do I get any solutions? What about the square root of a negative number? It's imaginary, right? So I don't get any real valued solutions. So the only vertical asymptote for this problem is t equals negative 2, although it factored into 3 factors down there. One of them canceled, which gave us a hole in the graph. One of them doesn't have any real value zeros, only imaginary, and those guys don't count. And then the single t equals negative 2 is our vertical asymptote. So I have another one. Find the vertical asymptote of f of x equals tangent of pi x. Okay. Now remember, vertical asymptote, numerator can't be 0, denominator is equal to 0. Are you staring at this and going, this does not even have a denominator? Why are we talking about this? Y'all, you know it does, right? So f of x is equivalent, tangent of pi x is the same as the sine of pi x. I always like to put parentheses around my argument and my trig function, divided by the cosine of pi x. Okay, it does have a denominator. You see it right there. So what I'm trying to do is I'm trying to find out where is the cosine of pi x equal to 0. That's the question. Now to answer like this is called a multiple angle problem. What you have to think about, this doesn't matter right this minute, where is cosine equal to 0? Now if you're a unit circle person, okay, I am, you ask yourself, where is cosine equal to 0? Well, cosine is 0, it's the x value, right? That happens up here, remember that is at pi over 2, and down here that's at 3 pi over 2, okay? So now I set pi x equal to pi over 2, and I set pi x equal to 3 pi over 2, and I really is supposed to add all the times this could happen. I didn't leave myself enough room for that. Because remember, you have to add 2n pi to that. I'm going to come over here. Pi over x equals 3 pi over 2 plus 2n pi. Now I'm solving for x. Okay? So I'm dividing everything by pi. Divide by pi, divide by pi, divide by pi. I'm going to simplify that. That gives me x is equal. That's the goal, is to get x by itself. Now pi over 2 divided by pi, the pi's cancel, so that gives me 1/2 plus, and these cancel, 2n. So that's one of, well, that's an infinite number of results. Remember, n are your integers. Okay, that's times around the circle. Over here, I'm also going to divide every term by pi, so I can get that x by itself. So that gives me x is equal to, now invert and multiply, those pi's cancel. That's 3/2 plus those pi's cancel, 2n. So my results are of that form. So what does that mean? Well, if I plug those values into sine, you know sine and cosine don't have the same 0 values at all. So if I take one of these, and we can list them, like if n is equal to 0, then that would give me x is equal to 1/2 down here, and x is equal to 3/2 up here. If n is equal to 1, that would give me, well, that'd be 1/2 plus 2, which would be 2.5, or you could say x is equal to 5/2, and x is equal to, over here, 3/2 plus 2 would be 2 and 3/2, or you could find a common denominator and say that's 7/2. Okay, now how many vertical asymptotes do you think we're going to have? Well, there's an infinite number of them. You can continue in this pattern forever and ever. So they are of this form. Can you see a pattern? So 1/2, 3/2, 5/2, 7/2. So it looks like odd numbers over 2. Those are going to be your vertical asymptote. Another way to write odd numbers, I don't know if you've ever thought about this, is 2n plus 1 over 2. 2n plus 1 is always an odd number, and then divided by 2, you've got it. I know, trig always makes everything hard, but the idea is still the same, right? You take your denominator, set it equal to 0. Okay, here's a great problem. Determine whether the graph of the function has a vertical asymptote or a removable discontinuity at x is equal to -1. So in other words, what in the world is going on at -1? Now, remember, a vertical asymptote, you could take the limit as x approaches -1. I almost wrote that wrong. Stand by. There we go. X approaches -1 from the left of this function. Okay, and then we're going to take the limit as x approaches -1 from the right of this function. Okay, now we need to simplify this. Does x squared minus 2x minus 8 factor? So we're trying to find numbers that multiply to be -8 and add to be -2. What do you think? So about x minus 4 times x plus 2 over x plus 1. Nothing cancels, right? What does that mean? If nothing cancels, or we plug in -1, we get a 0 in the denominator, and we would get -5 times +1, -5 in the numerator. That means that guy is a vertical asymptote. Okay, that's all it asked. It didn't actually ask us to find the limit, but the limit would go to, how could we figure that out? Okay, let's talk about that. If we go -1 from the left, let's just analyze this. If I plug a -1 into just this part, that is going to be and -1 from the left, so a number less than -1 minus 4 is a negative number. Do you agree? So it's a negative. How about if I plug in a number very close to -1, but on the left, again, of -1, so a little less than -1, and I add 2 to it, it's going to be positive. You agree? Okay. A little less than -1, not a lot less than -1, just a little. And then in the denominator, I plug in a number, again, a little less than -1, and I add 1 to it, that's still going to be negative. So overall, that gives me a positive answer, right? Negative on top, negative on bottom, positive. So that goes to plus infinity. It didn't ask that, okay? We just want to talk about the behavior of the graph. And let me solve this one in red. So again, it factors. You don't have to factor it if nothing cancels, but it makes this analysis that I'm doing right here a lot easier. So this time we're doing a number a little bigger than -1. Not a lot bigger, just a little. So a little bigger than -1 minus 4 is negative. Okay. A little bigger than -1 plus 2 is still negative. Just a little bigger. Okay. And then a little bigger than -1 plus 1 is positive. Okay. We have a negative times a negative divided by positive. That's also a plus infinity. And remember, if your limits go to plus or minus infinity, that means you have a vertical asymptote. Hey, I wonder if you caught my mistake. I just caught it. Check this out. So, it's on the second one. So I've got -1 from the right. So if I plug in a number a little bit bigger than -1, that's what from the right means, right? A little bit bigger than -1 plugged in here. So think -0.9. Plugged in here is definitely negative. I had that one right. A little bit bigger than -1, like -0.9 plugged in here. That is positive. I don't even know if I said negative, but I sure wrote negative. Okay. And then we had the denominator right. -0.9 plus 1 is positive. Okay. And a negative times a positive overall is a negative divided by positive. That gives us negative infinity, not positive infinity. You can get the same. I just had a feeling it was wrong, so I checked it out. Sure enough. Okay. So here's that question again, just a different function. Determine whether the graph of the function has a vertical asymptote or removable discontinuity at x equals to -1. Okay. Now if you plug -1 into this, just for the sake of doing this, we're going to handle it another way in a minute. I have the sine of -1 plus 1 divided by negative 1 plus 1. Well, denominator, we know we've got 0. So there's hope. It might be a vertical asymptote. Or it might be removable whenever you get 0 in the denominator. That's what's going on. But now the sign of 0, okay, remember your unit circle. Here's 0. The angle 0 right here. Sign is the y value, so that y value is also 0. Now that pretty much means it's not a vertical asymptote, right? It is a removable discontinuity. Moreover, I want to talk about taking the limit. If we take the limit as x approaches negative 1, remember if we have sine of x plus 1 over x plus 1, so we've got sine of x plus 1 over x plus 1, okay? So we already decided we got 0 over 0. That means to evaluate this limit, we have to simplify the function or use a trick. Now, I think you might remember that we have the theorem, if we have the limit as x goes to 0 of sine of x over x. Now, what was important is that these values had to match. Notice they match here, okay? But we're not taking the limit as x goes to 0, right? But it's the same idea. Like if we plug in 0 here, we get 0 over 0. This is a composite issue. This is like saying, since when we plug negative 1 in here, that gives us 0. This is the same exact idea of saying what we have right here. Okay? So this is equal to 1. For this very reason, the limit as x goes to 0, sine of x over x is equal to 1. Again, that's a theorem that we've already worked with. Okay, and you can even think about this as a theta value. Our theta value is x plus 1, and what makes x plus 1 equal to 0 is negative 1. It's an interesting trick. Now, we didn't have to use that to come up with our answer. We use the idea if you've got 0 over 0, that's going to give you a removable discontinuity, and that's what we used. So we want to wrap up this section by talking about properties of infinite limits. You see we have three properties here. What I want you to keep in mind, C and L are real numbers. Okay, C is an x value, L is a limit value. And the limit as x goes to C of f of x is an infinite limit. Remember, that means the limit does not exist, but it tells us how it doesn't exist. And the limit as x goes to C of g of x is L. So g of x has a regular real number limit value, whereas f of x goes to infinity. Notice it says sum or difference. If we add or subtract, the limit as x goes to C of f of x plus the limit as x goes to C of g of x. Okay, and if you think about that, what's going on here, it's like thinking about adding the limit as x goes to C of f of x is infinity, plus the limit as x goes to C of g of x is L. Now let's think about this. If you take infinity and add a fixed value to it, you still get infinity, don't you? Now you might think, well, you get a little bigger than infinity, or if L were negative, a little smaller than infinity, but it's still infinity. We're not talking about one infinity is bigger than another. It's still infinity. The second property says, and it's two different things. Let's look at the first one first. If we have the product, if we take the limit as x goes to C of f of x times g of x, that equals infinity as long as L is greater than or equal to 0. Now let's think about it. If we just look at the limit as x goes to C of f of x, okay, we know that's infinity. So that's like saying infinity times, and the limit as x goes to C of g of x, okay, is L. Then it goes on to say, as long as L is greater than 0, you have infinity times a positive number, and that equals infinity, right? Have to be infinity. On the other hand, the second situation, notice the order is the same, but it says that L is less than 0. So the limit as x goes to C of f of x is still infinity, but the limit as x goes to C of g of x is still L, but again, L is a negative number in this case. And infinity times a negative number is negative infinity. And then the third situation. you're going to use this a lot, by the way. If we have the limit as x goes to c of g of x divided by f of x. Remember, g of x, the limit as x goes to c of g of x is just a number, L. And the limit as x goes to c of f of x is infinity. Now, if you have a fixed number, like 5 over infinity or 10 over infinity, when you divide by infinity, right, that's huge. Okay, and the larger and larger this is, that goes to 0. So a number divided by infinity is 0. And again, that's going to come up again and again and again. So we have an example. Let's take a look. So we have the limit as x goes to 0 of 5 plus 1 over x. Okay, so that's the limit as x goes to 0 of 5 plus the limit as x goes to 0 of 1 over x. Now we talked about we're not allowed to use that sum difference property if the limits don't exist. But this brand new theorem says if the limit is infinity, then we can consider this. So what is the limit as x goes to 0 of 5? Remember, the limit of a constant is just that constant value. That's just 5. It's a horizontal line. Plus the limit as x goes to 0 of 1 over x. Okay, now we really need to split this up into two problems, or I should have asked you just from the right or just from the left, because it kind of matters. So let's change this just to the right to not overcomplicate the problem. Why? Because if we're coming from the left, these are negative, which means it would go to negative infinity. If we're coming from the right, these are positive, which means it's going to plus infinity. And I truly think that's what I meant. I just didn't type it correctly when I made my PowerPoint. So we have 5 plus infinity, and if you take infinity and add 5 to it, you're still going to get infinity. Now that's using that property, but it only makes sense, right? Alright, this is the last problem. Let's see what we can do with this problem. Now, to be able to use these properties, of course this would be sum or difference, we've got to know it meets these conditions. So I'm going to split this up, assuming that they both have limits, or one of them is maybe infinity. But you have to do this, and by this I mean split it up, to even know if you can use this. Okay, so that's what my goal is to figure this out. Now remember, we have substitution at our fingertips. You should always try substitution to see if it works. How do you know if it doesn't work? If you get a 0 in the denominator. So if I plug in 3 right here, okay, and really this is just a polynomial, it's a linear function. So I plug in 3, and that's fine. That gives me 1. I'll simplify that in a minute. Here, I just try to substitute in 3. So I left out the cotangent. There we go. So it'd be the cotangent of 3 of pi 3, I'm not writing this properly, so pi times 3 over 2. So that's what we have. Now the question is the cotangent of 3 pi over 2, is that infinity? We need to find out. So we know 3 over 3 is 1 plus. Now, if you know what the cotangent of 3 pi over 2 is, you jump right in there. If you want to use your calculator, you know, exact answers are good, but I would like to evaluate it by the knowledge that I have. So you all know that cotangent is cosine of 3 pi over 2 divided by sine. Remember, tangent, sine over cosine, so cotangent, its reciprocal, is cosine over sine. Now, the real question is this denominator equal to 0? It's actually not. So you got 1 plus the cosine of 3 pi over 2. Now, remember where 3 pi over 2 is. That's down here. Cosine is the x value around the unit circle. So the cosine is 0 divided by the sine of 3 pi over 2. And the sine right there is negative 1. So that's not an infinity at all. That would be 1 plus 0. So the answer is 0. This matter of fact, this could have shown up in section 1.3. Just regular old properties of limits. Infinity did not have anything to do with this. Now, had I changed this problem to tangent of pi x over 2, we would have a different animal. Okay? Try that problem. See what you think, and let me know if you have trouble with it. Change it to tangent. All right. I hope this helps. Let me know if you have questions.